So what we have here is a KUKA KR5 common industrial robot, a smaller version so it fits in our lab. And then we have a TMAC made by Leica mounted on the end. The beauty of the TMAC is that you get a 6 degree of freedom measurement of the end effector very quickly. You could also do this with any instrument that could measure even a single point on the end effector, but having 6 degree of freedom measurement just makes it quicker to do a calibration because you get more information with each measurement. So most of these robots, the lion's share of them in the industry, are not used in a kinematically controlled way. And what we mean by that is they're used typically to store a series of joint positions and then play them back. So what we're trying to do here, more and more in production, is to take robots and make them more accurate so you can do drilling and things like that with kinematic precision. So there's several ways to do that. Out of the box, the robots typically aren't calibrated very well. They have nominal values, and maybe they're good to a 1/4 inch or a 1/2 inch. Sometimes better if you opt for an option where the manufacturer calibrates the robot. But even still, they aren't typically full field calibrated for your application. So you sort of have two options. You can either calibrate the robot very well, and we'll do that in this video, or you can do corrections of the motion at the time you're actually ready to drill. Both of those are good options, and in fact the corrections work better when you have a good calibration of the robot. So what you're going to see is that we'll move the robot to a series of positions, measure the end effector, run a calibration, which is a pretty quick, painless process. Once that's done, we can then move the robot under our kinematic control, and then we'll demonstrate a kind of a move, measure, correct, where the TMAC measurements are used in situ to do a quick correction before drilling or some other operation would take place. So here we're going to start the SA machine interface from a fresh spatial analyzer job. To do that, we have to add two components. We have to add an instrument, and then we're also going to add a robot, in this case the KUKA KR5. So the first thing we'll do is we'll add the instrument, and we'll pick the Leica tracker since we're using the TMAC. That's added to our model. Now we need to add the robot as well. To do that, robots and machines. You can add a machine. There's several ways to do this. One of the easiest is to load an SA machine file, which has the kinematics and the graphics all combined. So we have several of those available. Here's one that's the KR5 with the TMAC on the tool. We'll go ahead and open that. Now you can see the robot position. We'll go ahead and shade it. So again, the two are not located in any specific way. That's part of what we're going to do in the calibration. But first we need to connect the tracker interface to the tracker and the robot interface to the robot. This is something you could automate, but for purposes of demonstration, we'll do it step by step. So first let's do the tracker. So we run the tracker interface, pick our connection, let it start up. Okay, so now we have the tracker interface connected and ready to measure. Then we're going to go ahead and start the robot driver. There's a few more steps in doing this because part of starting a robot program is getting to a safe position. So we'll run the robot driver. Now we need to connect. It's just like an instrument interface. You can choose which SA and which robot or machine you want to connect to. So we're going to hit the connect button and we have to go pick which robot. We could have multiple ones in the job. When we say connect here, now it's going to wait for the controller. Well, I have to go over to the teach pendant and hold a safety button, which moves the robot to the home position. This is not essential, but it's a good first step. Once it gets there, we hit the button again, and then we're connected. At that point, we now have control of the robot, and we can move it to many different positions, do what we need to do. For calibration, we have a lot of poses we'll go to, but basically, we're in control of the robot. So if I go to a joint drive window, I could move the joints one at a time. For example, I could move the, let's say the elbow down, so that would be a negative, I believe, rotation. I'm moving the roll, so I can move the roll, or I can move the elbow here. There's up, there's down. Now the beeping sound is because the TMAC can't see the tracker. So I could rotate the TMAC into position, or I have some other pre-stored files I could load that are just a series of positions. And I can just move to those one at a time. All right, so what we're showing here is the spatial analyzer machine interface, and specifically we're going to show robot calibration using a Leica TMAC and a KUKA KR5 robot. So what we're going to do, you can see a model of the robot in the SA job right here, and there's a TMAC on the end of that. And then you can also see the laser tracker. So what we're going to do is we're going to make a new calibration, move the robot through a series of poses, and record a matching set of end effector locations and robot poses. So I'm going to add a new calibration. I'll call this video demo. Now what we do is we say we want to trap measurements into that calibration. So now we have an interface connecting to the robot and we have an interface connecting to the TMAC. So I'm going to move the robot to a series of positions that I've pre-recorded. And at each position, I'm going to go take a measurement from the TMAC. And what you'll see is every time I do that, it adds a pose to my calibration. So I just move to the next one. Once it gets there, I take another measurement, and I just keep going. And typically when you do this, you want to select a series of poses that represent the workspace you're going to be working in for the robot, so you get the best, most meaningful calibration. And the nice thing that's going on here is because of the integration, when I hit measure on the laser tracker interface, SA is saying, okay, I have a measurement for that pose, but now I need a joint angle set. So it sends it back to our robot interface to get an immediate read on all the joints so that the data is synchronized. Now we'll get some poses a little higher in the workspace. Do a little wrist roll. And maybe one or two more. And this one. Okay, so now we have 14 poses that we can run a calibration with. Now what we're going to do is we're going to stop trapping, and what that does is any more measurements that come in won't get added to our calibration. So now to actually run the calibration, what we're going to do is we're going to just right click on the calibration we just stored and run the calibration interface. In this interface you can see all the different components of the robot. So those are kind of your unknown variables. We're solving for those things. And if you look at each of these, like the shoulder joint, for example, there's a window that shows the Denevit-Hartenberg parameters of that joint and then which variables we're going to vary as part of this calibration. Same thing for all the different joints of the robot. But what we're going to do is we can look at these points over here. These are our measurements of the manipulator. And notice there's very large errors. Well, that's because we haven't done any calibration yet. We don't really know where the robot is. So first thing we're going to do is rough fit the robot. That basically takes all the tip measurements and does a quick best fit, ignoring the calibration of the robot, just to get us kind of in the ballpark. Once we have that, we can calibrate the base of the robot here in 6 degrees of freedom, and we can calibrate the tool. And the reason we're going to pick 6 degrees of freedom instead of XYZ is because we have a TMAC on the end measuring the full 6 degrees of freedom. So we run that calibration, we get some pretty good results, about 37 thousandths, but notice the robot is fixed. We've done nothing yet to vary the kinematics of the robot. So what we're going to do is we're going to click on partial and hit run. So now we've added a few more degrees of freedom. We have 23 variables, 84 equations. That's a pretty good calibration. If we go to full, that also adds the stiffness parameters of the robot to the calibration, and I can run it again. So now we're down to about 19 thousandths of an inch RMS in position and 0.07 degrees in orientation. Now another nice thing is we can sort these errors by their size, by their columns, and then we can click on these poses and we can see the graphical representation move through the poses. In case you wanted to determine if a pose, like you can see one of our highest errors is when we're reaching way up high. And that's because we're moving to a different area of the workspace than some of these other points. But anyway, in this case, we don't see any direct outliers. There's also a report we can generate that has all this information. But for now, we'll just go ahead and apply the calibration to the robot. So now what happened is the kinematics in Spatial Analyzer now have that new model. So what we're going to do is now we're going to use this calibration to do a kind of a move measure correct on the fixture. So to do that, we're going to first move to sort of a safe position to start with. Now what we're going to do is we're going to guide the robot to a position above this fixture and then try to plunge to the hole. And we're going to use the TMAC live to do a correction. So what we're going to do, I'll zoom in a little bit in the graphics here. We're going to run a measurement plan. And before I run it, I'll actually show you a little bit of the commands used in this measurement plan. So the measurement plan we want to look at. And you could do a lot more advanced implementation of this, but just for the purposes of demonstration, we're going to move the robot to a frame we've predefined. Then we're going to move it to a goal frame. And that goal frame should be right above the hole on the part. But then what we're going to do is there's a little bit of a loop we start up where we measure where the end effector is with the TMAC. And once we measure, then we go ahead and do a correction. So we're going to take a measurement. Then down here, we're going to actually compute a correction frame. And there we take the last goal frame we wanted to go to, the adjusted goal frame, and then we compute where we actually want to go. And then we're going to actually do the move and then come back and compare it again. So let's go ahead and we'll run that measurement plan. You can see the robot move. And now it's gotten to a plunge position, but it hasn't done any correction. So what it's come back and told me is the magnitude error is about 1/10 of an inch. So then we're going to do a refinement of the position. You can see the minor move that's done there. Now we're coming back about 0.1/10 of an inch. So again, what's happening in that cycle is we're moving the robot, commanding the TMAC to measure, and then comparing where we are with where we want to be. And you can do this in an automated loop, but just for the purposes of demonstration, we're doing it step by step. So we can refine position again. Now we're down to about 0.2 of an inch. That gets to be about the limit of the robot's encoder's ability to position. So sometimes you can do a little better than that, sometimes not. There we're down to about 0.1/1000. But you're getting down to the area where you can't do much better just because of the manipulator's repeatability. So that's a quick showing of how you move and correct. The other piece of this is that we have the kinematic control of the robot in Spatial Analyzer. So we can do some sort of neat things like teach pendant type motion with the robot. So in SA, we can right click the robot and we can pull up our teach pendant. And this is similar to a teach pendant you might find on a common industrial robot, except that it uses the calibrated kinematics in SA. So if we want to do motion in, let's say, the tool coordinate system, we can go in the -Z and we'll pull up graphically. We can look at the motion and see if we like it. If we like the motion, we hit drive and the robot makes a move. So that's kind of neat in that we can do all the different components of the tool. Do a little bit of Y, a little bit of X. Now all these destinations are of course using the fully calibrated kinematics. Now the other thing we can do is we can drag the end effector using the mouse. So we can hold down Control Shift and then click on the tool, and as we move, the robot follows us graphically. If we get to a position we like, we say drive. This lets you very easily move the robot to different locations. You can also use it to rotate the tool. And of course you can control it through the teach pendant as well. So that's a quick showing of the kind of control we have through SA of the robot, quick showing of the calibration process, and the move, measure, correct process as well.